Hello, welcome back to 10 Minute Science. Today I'm incredibly excited to share with you news from Lawrence Livermore National Laboratory at the National Ignition Facility, where they have for the first time ever in any experiment in the history of mankind achieved nuclear fusion in such a way where the energy coming out of the nuclear fusion reaction is larger than or exceeding the energy going into the experiment. So it's sort of a net positive energy output for the very first time in fusion. So it's our very first step on the way to harnessing the energy source that we all know exists inside of the sun. Now inside of the sun, it's gravity compressing all of the hydrogen and other elements there, compressing them in so much to achieve nuclear fusion the nuclei in the atoms there, generating a lot of heat and light in the process. Of course, the star is so large, gravity can do that for us. We want to build a power source on the planet that can achieve nuclear fusion at a smaller scale because without having the mass of a star, right? And with that, we'll have cleaner energy, independence from fossil fuels, and so on. It's a very clean power source, actually, fusion, and so we want to be able to figure out a way to harness that. This is a first step in that direction. All right, so I want to go through the facts with you, and then I'll show you a lot of construction photos and how it was built, and then at the end of this video here, we'll talk about fusion in general and how does fusing two atoms together actually generate heat and light and energy in the first place. We'll have a basic lesson on that. All right, so National Ignition Facility. Basic idea is what they did is they have lasers surrounding a chamber. In the center of a chamber is a fuel pellet. We'll talk a lot more about what's inside of that pellet in a few minutes. But the lasers heat up and compress the fuel pellet, and it starts the chain reaction of fusion. And what you want to do is you want to make enough fusion energy so that the energy coming out of the fusion continues to heat up and compress the pellet further, generating more and more and more fusion. So that's what you want. You want a chain reaction to happen, just like is what's going on in the sun, where some of the energy coming out is further heating the fuel and then causing further fusion reactions to continue the process along. That's how we would generate and use it for a nuclear power plant. So in their experiment, they put 2 megajoules of energy into the system, 2 megajoules of energy into their fuel pellet, and got about 3 megajoules out. Now I'm rounding here. It's really not exactly 2 and 3, but it's very, very close. So 2 megajoules in, 3 megajoules out. Now, what is a megajoule, right? So let's just talk for just a second. A joule is a unit of energy, so a megajoule is millions of joules. So 2 million joules going in, 3 million joules going out. What is a joule? Well, if you remember from physics, work is equal to force times distance. And so the unit of work is joules, the unit of force is newtons, and the unit of distance is meters. All right, so 1 joule is the amount of energy that would be required to take a mass or to move a mass a distance of 1 meter by pushing on it with 1 Newton of force. So if you take something and push on it with 1 Newton of force and it moves 1 meter, then you've used 1 joule of energy to do that. So do these units make sense? Basically, if you hold an apple in your hand, that's about 1 Newton of force. The gravity of the earth is you're feeling in your hand. So if you can imagine pushing on something with a force equal to about what you feel in your hand from an apple, that's about a Newton of force. And if you push and it moves for 1 meter in distance, then you've used about 1 joule of energy. So about 1 joule of energy is essentially pushing with that small amount of force that you get from an apple over 1 meter of distance. So the laser put 2 million of those joules in to start the reaction, and the fusion released 3 million of those joules out. It's just a first step, but every journey begins with a first step. All right, so let's go through a few more facts about what their setup is. They've been building this facility for 20, 25 years, slowly increasing the power of the laser system used to start the reaction. And by the way, the lasers used in this facility are the largest laser systems ever built by mankind. Millions of joules of laser is not something you just go purchase from the store. It's something you have to design and improve over the years, many, many decades actually. So they start with a pellet that's about 2 millimeters in diameter. Inside the pellet is hydrogen. but it's a special flavor of hydrogen that's different than normal hydrogen because there's an extra neutron in the nucleus, either one or two extra neutrons in the nucleus. I'll talk a little more about that later. Basically, it's either called regular hydrogen is called hydrogen. When you add an extra neutron, it's called deuterium. And when you add two extra neutrons into the nucleus of the hydrogen atom, it's called tritium. So this target pellet had a mixture of deuterium and tritium, which are just different isotopes of hydrogen inside the pellet. And of course, it's super cooled, very dense, and all this kind of thing, a very small little package. And then the facility has 192 lasers, which are of these megajoule, actually the lasers themselves are even bigger than that, and the hundreds of megajoules of energy, pointed, 192 of them pointed and focused on this pellet, which is inside of a cylindrical container. All right, the 192 lasers fire in a very precise timing, and they actually fire at the casing, the cylindrical casing. There's kind of like a, sort of like a cylinder like this, and inside is this little pellet. 192 lasers are pointed in all different directions, and they actually focus on the actual cylindrical object around the pellet itself. And they dump all of that energy into the inner walls of this cylinder surrounding the pellet. The time it takes to dump all that energy in there is the time it takes for the speed of light to travel 10 feet, right? So think about the speed of light, 3 times 10 to the 8 meters per second. A light beam can go around the planet Earth 7 times, 1, 2, 3, 4, 5, 6, 7 times in 1 second. So this energy from all this lasers are dumped into the walls of this, essentially the container housing the pellet, in the time that it takes light to only move 10 feet. That's incredibly fast. It dumps all the energy in incredibly fast. Now the energy going into this generates a lot of X-rays. The X-rays get focused on the pellet and they instantly turn that pellet into a plasma, stripping the electrons off, and so you have a soup of the nuclei of the deuterium and tritium along with the electrons, and then it gets compressed, and the fusion happens when you can compress that mixture for long enough at a high enough density and at a high enough temperature and for a long enough period of time so that two or more of those nuclei will fuse and release some energy in the process. All right. And this is called inertial confinement fusion. Inertial confinement because it's confined due to its own inertia, all the lasers hitting from all different directions essentially. This is in contrast to another type of fusion reactor that we're trying to build called magnetic confinement. Magnetic confinement uses magnets to squeeze the plasma and to kind of get it to fuse. Inertial confinement basically uses the inertia of the object and lasers hitting it from all sides to start the fusion process. Now, what I'd like to do now is talk about how they built this thing because it's absolutely incredible that we could build something this massive to pull off an experiment. So first of all, the completed machine you can see right here has a chamber and all of these cylindrical tubes going in. This is carrying the laser energy into the interior of the machine into a target chamber on the inside. So lasers are going in. At the inside of all of this, in the central point, is the pellet containing the tiny, tiny amount of fuel. Now this pellet is only a couple of millimeters across, so it's like half the size of a peppercorn that you would grind up in your kitchen. Very small pellet of fuel there. And that pellet contains deuterium and tritium, which are different flavors of hydrogen. I'll talk a little bit more about that in a few minutes. Now, once the ignition happens, there's a chain reaction that happens where you have fusion of some or a small fraction of the deuterium and tritium releasing energy, right? That energy further goes into heating up nearby and compressing nearby atoms and causing nearby nuclei to fuse, and then the process continues, and the idea is you want a chain reaction, a self-sustaining chain reaction where you get more energy out than you're putting in from your laser system. The sun does the compression by gravity. We're doing it by lasers because we don't have the mass of the star to squeeze it all together. All right, so here's a picture of the target chamber. The target chamber, this is a picture under construction. It's comprised of 10 centimeter thick aluminum panels. So that's built there, and you can see how it all goes together with the scale of people right there, so you can see how kind of like large the thing is. Here's a picture of the housing for the target chamber and the optics that go along with everything, because the lasers have to be focused very, very precisely on the target chamber. And the housing for the target chamber is 10 meters in diameter, so about 33 feet. Now here's a picture of lowering this entire thing, this target chamber, into the ground, and you can see all the beam ports, all the cylindrical beam ports where the lasers will go in, and also the diagnostic equipment will be able to see and take measurements of what's going on inside here. All right, now here we have the target chamber in place. It's now lowered into position, and the 7-story walls are then erected around the target chamber, so just kind of giving a scale of how big this thing is. It's a very large experiment, okay? Now here's a picture of the interior of the target chamber. You can see the sort of the spherical nature of it from the inside with the people there. You can see the scale of it and the, of course, the cylindrical little holes there where the lasers are coming in. Again, 192 laser beams, the largest lasers ever built, focused on this tiny little 2mm diameter pellet. That's what the machine is. Now here's a picture of the completed machine, and you can just see the scale of it. This is just a small zoomed in picture, but you can see the lasers kind of focused onto this central position inside the target chamber. Now, after they've achieved this incredible achievement, this is like decades in the making, right? What are the next steps? That's what they're trying to figure out. The immediate next steps is to try to improve the efficiency of the lasers. Right now, the lasers take a lot of energy to a lot of power to generate the energy to focus it. So how can we do that in a more efficient manner? Also, after the pellet vaporizes, what do you do next? Do you put another pellet in there and vaporize that one? Do you have multiple pellets all sitting around and focus your lasers on different pellets? What is the best path forward? I don't think they know the answers to these questions yet. I think there's a lot of experiments that will need to be done to figure out a path to commercialization of this process, but that sort of isn't the point. The point is that we know we can build a fusion reactor. We know we can because they just demonstrated it. That's why it's a big deal. Once you demonstrate something, you know it's possible, it's much easier to open the door going forward. All right? And the last thing I'll say before we go into the lesson on fusion there is basic research is sometimes people don't understand sometimes why we do basic research, right? Because they can't see the point of it. Like, why develop quantum mechanics? Who cares about quantum mechanics, right? Well, lasers are made possible by quantum mechanics. Quantum mechanics is basically understanding how atoms work, how electrons work. And if we don't understand how they work, we can't build lasers to make these intense beams of light, right? And right now, even if this type of nuclear fusion project doesn't make a commercial reactor next year or the year after, we have still learned how to develop high-power laser systems, right? And some of the proposals out there for deflecting asteroids that might be on a collision course with Earth, for instance, is using high-power laser systems. So I guess what I'm trying to say is you cannot predict ahead of time what you're going to use or be able to utilize your basic research for. They never could have predicted that quantum mechanics would lead to the development of lasers. They weren't trying to make lasers, but it just happened. And that lasers could then be used for fusion research and also to deflect asteroids in space to save the Earth from a collision or something like this. But you can't predict ahead of time, but that's why it's important to fund and develop basic research, because you never know what might lead to medical developments or other developments from basic physics and chemistry research. All right, you can't predict the uses. All right, so now I want to talk just a little bit about fusion. Fusion is incredibly complex. People spend their entire career trying to figure out how to get things to fuse together. But I think I can explain in just a couple of seconds essentially how it works. So we have hydrogen is the simplest element on the periodic table. So I'm going to put H. That H is hydrogen, okay? Now a hydrogen atom is a single proton in the nucleus and a single electron orbiting the nucleus. Now, this picture of an electron orbiting like a solar system is not correct. An electron is really a wave function that surrounds the atom and all of this, but we're not going to draw waves. I'm just going to draw it like this because it's easier to visualize, okay? Now, this is a hydrogen atom. It turns out there's another stable isotope of hydrogen where there's one proton there and a single neutron. The neutron doesn't have any charge. It's neutral, that's why it's called a neutron. So there's a single electron here orbiting, and this thing, right, is called deuterium. I could spell it out, but there's no real point to it. I'll just put deuterium. You can look it up if you want. It's not too hard to spell, but it's just a long word here. So I'm going to put D here. All right, this is a stable isotope. It's just a heavier version of hydrogen. Still one positive charge, one negative charge, but you have extra mass in the nucleus, right? Because the mass of the neutron and the proton are almost the same. It turns out we can add yet another neutron here. to make another isotope, which is also stable. So here we have 2 neutrons, right? And again, there's only 1 electron because there's only one positive proton there. We only need 1 electron out here. And this one, this isotope is called tritium. Tri for tritium. So you see 3 things in the nucleus, we'll call it tritium. 2 things in the nucleus, we call it deuterium. Right? And the single is hydrogen. These are all hydrogen. They will all react chemically the same way hydrogen will react. They have 1 electron on the outer shell, but they're heavier, right? Because you add an extra neutron, you double the mass of the nucleus. You add 2 neutrons, you effectively triple the mass of the nucleus. So the pellet that they use in this facility to initiate the inertial confinement fusion, they're not using regular hydrogen. They're using tritium over here and deuterium, a mixture of tritium and deuterium. Why do they do that? We could go and spend your entire life studying the math behind it. We're not going to do the math. I'm going to talk at a big top level why we would care about that. What we have here is a white ball, which I want you to pretend is a hydrogen atom. It's a hydrogen atom here, which means that inside of this thing is a positive proton and 1 single electron. And here's another hydrogen atom, right? And so inside of here, positive proton, electron surrounding it. All right. Now, you can pretend that this is deuterium and tritium if you want. You just have extra neutrons in the nucleus, but otherwise they're going to behave the exact same way. What I want you to focus on is that inside the nucleus here, you have 1 proton. Notice there's 1 proton in every one of these situations, but protons are positive. So once the laser shoots its energy into the substance there, all of the electrons get ripped off the outside and they're free electrons, and these nuclei, these hydrogen nuclei or deuterium nuclei, are just running around bouncing off of everything in there. Everything's very, very hot, okay? However, they still have a positive charge, a single positive charge in there. Now, you may not know this, but the repulsive nature, because remember, opposites attract and positive or like charges repel, right? Same charges repel. 2 positive nuclei are going to repel each other, okay? Now, it turns out that the electric force, all of these electric forces, they're millions and millions and millions of times stronger than gravity. We think of gravity as a strong force because it holds us to the ground, but it's really not that strong. It only affects us materially because the entire planet is pulling on me. It takes the entire Earth pulling on me for me to feel the weight that I have, right? But actually, the positive repulsion of electric charges, or attraction if they're opposite, is millions and millions and millions of times stronger than gravity. So if I have 2 protons here, or 2 deuterium nuclei, or 1 deuterium nuclei and 1 tritium nuclei, the electron's gone. We've already ripped it apart with the lasers, and we've turned this into a plasma, so we have these guys running around. We want to push them together to cause them to fuse, to make a heavier element. Because as we go down the periodic table, everything has more neutrons and more protons. So if we can squeeze them together and force them to stay together, they'll form a heavier element, okay? But the problem is that they both have positive charges here, positive, positive, and they're millions and millions of times stronger than gravity. So if I push and push and push and push and push, it's going to repel, 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 repel. It's incredibly strong, incredibly difficult to overcome the repulsive nature. If I forget the electron, if I bring these together, the repulsive nature of the 2 positive protons there is going to push so hard. It's very, very difficult to get these guys to overcome that and to get them to touch, for lack of a better word. But here's the kicker. As strong as the electric forces are, millions of times stronger than gravity is what I'm telling you, right? There's something even stronger than that. And that is called the strong nuclear force. So, the strong nuclear force. Have you ever wondered, in the periodic table, when you go down to like a heavier element like oxygen, lots of protons in the nucleus. There's some neutrons there too, lots of protons. If the protons are trying to push against each other, how can the nucleus stay together? The nucleus is full of positive charges and they're practically touching each other. How can they stay together? Well, because even though they're repelling each other with millions of times the force of gravity, millions and millions and millions of times the force of gravity, there's a force of nature even stronger than the electric repulsive force, and that is called the strong nuclear force. But there's one catch. the strong nuclear force is a very short-range force. So whereas electric forces can act farther away, the strong nuclear force is millions of times stronger than that force, stronger than the electric force, but it only acts. It's only able to act over distances inside the nucleus. You might remember from physics and chemistry, the nucleus is very, very small compared to the size of the atom. So the strong nuclear force is much stronger than the other forces of nature, but it only acts inside the nucleus or on the distances of a nucleus. If you get things farther apart than a nucleus, then it just doesn't do anything, and then it isn't strong enough to reach out that far, and so the electric repulsion pushes everything away. But if I can push so hard against this electric repulsion that I can get it inside of the effective range of the strong nuclear force, then suddenly that nuclear strong force is going to dominate everything and suck them together, even though they're both positive charges. And when that happens, they're going to slam together and form a new nucleus. And then a lot of energy is going to come out, because think about these things just slamming into each other. A lot of energy is going to go into the particles. Photons will come out, and radiation will come out, neutrons will come out, and so on. And then you have a lot of energy. That energy that came out of this fusion reaction will go right into the next pair of tritium and deuterium nuclei that are there, and hopefully force them together to do the same thing again. And then more energy comes out, and then the next pair, and the next pair, and the next pair, and the next pair, causing a chain reaction of fusion, which is what's going on all the time in the sun, 24 hours a day. So if you wanted to think about it as something you can visualize, this is not a scientific drawing. This is not a drawing that I want you to say, oh, Jason said this is exactly what it is. I'm just telling you a way to visualize it. What you have here is sort of the force, on this axis, like the force required, or the force required to push these things together, right? As you bring them together, the force required, right? So you push and push and push higher and higher and higher and higher and higher. Eventually, if you get them close enough together, the strong nuclear force takes over, and then suddenly they're not repelling anymore. And then there's a huge trough down here at the bottom where they're going to slam together. So what I'm trying to illustrate here is not like a scientifically accurate physics picture of the energy of the situation. I'm just simply saying it represents pushing and pushing, repulsive, repulsive, repulsive. And if you can get over the hump, then suddenly whee down all the way into the valley. You go over a roller coaster. You have to put energy in to get to the top of the roller coaster. Then you can just ride it all the way down, maybe much lower than the top there. If you can push these things close together so the strong force can take over, then they can slam into each other. That energy of slamming into each other and releasing the particles and the photons in the process is what is liberated during nuclear fusion. That's what they got to happen. And they got it to happen by taking 192 lasers and focusing it on a point that was full of these atoms. By the way, they used deuterium and tritium instead of just hydrogen because it basically is hydrogen with extra mass. The strong nuclear force is generated by protons and neutrons in the nucleus. So by having extra neutrons, you can get them. You can have more strong nuclear force generated and a better chance of getting them fused together, because neutrons and protons together generate the strong nuclear force. So you want more of them in order to have a chance to get it to take, for lack of a better word, and draw them together and form a new nucleus, a helium nuclei. All right, so that's it. Big, big discovery. I encourage you to follow up on it as the years go by and see what happens with fusion research. It's been the holy grail of energy generation. I'm going to be following it. I hope you do the same as we move forward. And I also hope that you agree and understand, as I do, that sometimes funding basic research that you can't really see why we're doing it, or maybe you don't see the commercial impact of it, sometimes can lead to amazing results.